Heat change during a change of state. So a change of state would be melting, freezing, boiling, condensing. When you heat up a substance, add or remove heat, the substance is going to change one of two things. It's either going to change its temperature, go from 40 degrees to 50 degrees, or the other thing it can do is it can change its state. It can melt, it can freeze. I guess it wouldn't freeze if you were adding heat, but if you were removing or adding heat, you could freeze, boil, melt, condense. So which of these things is going to happen? Well, the answer is when you add or subtract heat from a substance, it is going to change its temperature most of the time, unless it happens to already be at its melting, freezing, boiling, condensing point. So the example that we all know is water. We all know that the temperature at which water boils, freezes, is 100 0. So we can go ahead and look at this on a graph. So let's consider a graph. Let's make a graph, and we're going to plot temperature on the y-axis and heat added to the x-axis. So as we go forward on the right, that's like we heat. So imagine that we just take some water or whatever and put it on a stove. The longer it's been on that stove, the more heat it's received, and let's going to see what happens to that temperature. And let's go ahead and, since it's water we're using, let's go ahead and put the important temperatures, 0 and 100 degrees Celsius. Those are the melting and boiling points of water. So let's go ahead and start right here. We're going to start with negative 20 degree water. We all know that water freezes at 0, but once it's ice, it actually can become colder than that. Let's start it at negative 20. So here's our water. And negative 20 degree water, known as ice, we're going to add heat. And as we add heat to ice, it's not going to melt, it's going to raise its temperature because it has to get up to 0 before it can melt. So that purple line there represents the temperature as we add heat to that ice, and it's going to keep going up until it gets to its melting point. Now that it's up at this 0 degree line, we're going to see that it cannot go above that line and remain ice. So what's going to happen is, as we add heat to it, it's not going to change its temperature anymore. It's going to remain at 0 degrees Celsius until all of the ice has melted. So we're going to continue to add heat, represented by the horizontal green line. So we're continuing to add heat, but the temperature is not going up. And this is going to continue until all of the ice is melted. So now at some point we've added enough heat that all of that ice has become melted water, and when you add heat to melted water, it's going to increase its temperature again. So as we add heat to the melted water, it's going to climb the temperature scale again. But you will notice though that the slope over here of the ice and the slope of the heating of the liquid water are not the same. You can pull them out and compare them. You see those slopes are not the same. So remember that the slope here is related to the specific heat of the substance. The specific heat determines how much heat you have to put into it in order to make its temperature go up. So that's going to relate to slope here. And so those are going to be a little bit different. I believe my graphic is a little bit messed. Oh no, it's good. The slope should be steeper for the not liquid. The liquid should take the most heat to raise the temperature. So that's good. So let's keep going on here. Let's keep adding heat. You can see that it's going to continue to increase temperature at that constant rate until it hits the next phase change temperature, 100 degrees Celsius. We can see that now that we're 100 degrees Celsius, it's not going to continue going up. Now it's going to change state again. So you can see when we hit these flat lines on the curves, these horizontal lines, temperature is not going up because the heat is going into changing the state. It's changing that liquid water into steam, we would call it. And that's going to continue. And as we continue to boil it away, we keep adding heat until all the water is boiled away, and then after all the water is boiled away, it's going to go up again, and that's steam. That we're basically taking hot steam and we're making it even hotter as we add heat to this system now. So if we stop and look back, each of the purple lines that we have here is a time when the substance is increasing its temperature. So those parts of the graph are going to be governed by the heat given in that section can be found using the formula mc delta T, which you should have already been introduced to before you watched this lesson. But the other thing to remember here is because they're different phases, those are different C values. It's like, I believe this first section has a C value of 2020. This middle section is 4180, and this is 2060, I think. I could be getting the steam versus ice backwards, but I think that's right. We'll see in a little bit. But what happens at these horizontal places? How do we find the heat necessary? We see that heat did go in there, but how do you calculate it? Well, here the heat only depends on two things. One, how much mass there was. It obviously takes a different amount of heat to melt big things versus small things. And it's also going to depend on the substance. It's going to take a different amount of heat to melt, say, lead than it would water or iron. So, yeah, there's some graphics catching up with the things I just said. So the heat change during a change of state, melting, boiling, freezing, condensing, is given by the following formula. Q, which is heat, is equal to M times H. Now this is very, very general because it can stand for any phase change of any substance. But H is a constant, so you're going to be given H in a problem unless it gives you all the other information that you calculate it with. But H is generally going to find it on a table. And if you're in my class, you can get this table out of your book, out of the chapter. And the H is going to depend on, one, what type of substances. You'd go and look and find H for water, or H for iron, or H for whatever substances that you're doing. But also, it's going to depend on the phase change. It takes a different amount of heat to boil water than it does to melt water. Those are different values. So the heat given by this change interaction is different than the heat for this change interaction. And you can see that that's represented by different lengths of the line here. Now, I might have gotten these backwards in terms of which one should have been longer, but I wasn't really paying attention to that when I made it. So we have different names for these H's. If you're melting or freezing, again, doesn't matter if I'm going this way or that way. If I melt or freeze, this heat is governed by H sub F, which stands for the heat of fusion. Fusion is what we call it, whether you're melting or freezing. A lot of times people think it's the heat of freezing, but it's actually fusion. So the heat of fusion for water, I think it's like 334,000 joules or something per kilogram. But a thing to remember is that if you're freezing something, it's a negative value, and if you're melting it, it's a positive value. So same for HV, heat of vaporization. This is the one associated with the liquid to gas phase change. And again, it's negative if you're going this way, positive if you're going that way. Negative for condensing, positive for boiling. So it should be obvious that melting and freezing would have the same constant, require the same amount of heat. The amount of heat to do this should be the same as the amount of heat to do that. Oops, sorry, went the wrong way. Anticlimactic. So melting, you're going this way on the curve. Freezing, you're going this way on the curve, but you're surpassing the same amount of heat. And that logic would also hold for the vaporization. So there you go. I talked too fast. So there's our formula for this interaction, Q equals M times H sub F. And up here, it would be heat equals M times H sub V. So we just look those numbers up, multiply it by the kilograms of water, and we'd be done. So we can actually calculate the heat at that first little slope, Q equals MC delta T. Here it's also Q equals MC delta T, different C's though. And up here at the top, Q equals MC delta T. Here we're heating ice, here we're heating water, here we're heating steam, here we're melting the water, here we're heating the water. And so now we can return to the I guess I didn't ask this question at the beginning, but this is kind of a question that our graph is answering. How much heat is required if we were going to turn 3 kilograms of negative 20 degree ice into 130 degree steam? So plot that on our graph here. Our first little interaction, Q equals MC delta T. We can plug that in. The mass is 3. The C for ice is 2060. And the temperature change, final minus initial, 0 minus negative 20 is positive 20. Be careful with your signs here. Gives us a heat value of 123,600 joules. Now that it's at the 0 degrees, we can melt it, so we can plug in our numbers into this formula. 3 kilograms times 334,000. Again, this number came off of a table in our book, and that's going to give us that number, just a tad over 1 million joules. Now we're going to plug our numbers into the heating up the water part of the graph. 3 kilograms times 4180, specific heat of water, times, again, positive 100. If we were cooling it, it'd be a negative value there, and the heat would be lost, which spits out 1,254,000 joules. And then finally, for our last phase change, we got 3 times the heat of vaporization of water. Notice that it's 2.26 million compared to 334,000 for the fusion. It takes much more more heat to evaporate, to vaporize water than it does to melt it. So this should have been a much longer green line, and this one should have been shorter, about 8 times as long or so. So forgive me for that. So 6.78 million joules is what that comes out to. And then finally we're going to heat up the steam, because we don't stop at 100 degrees. That's the heat of the steam when we make it. We're going to heat it all the way up to 130. So that's going to get it up to 3 kilograms times 2020. That's the specific heat of steam. You see it's close but not quite the same as ice. And then again positive 30, because we're going 130 minus 100 to get us that last term, which is, oh yeah, there we go, 181,800 joules. So those are all of our heats, all of those numbers that I just calculated. I'm just going to add them up, add all those heats up, and that's how much total heat it takes to turn negative 20 degree ice into 130 degree steam if you have 3 kilograms of it, which comes out to a really big number, 9,341,400 joules, which I'm going to write in megajoules, save myself some digits there. I'm sure I can't justify these sig figs, probably can only justify like 1 or 2, so call it 9 megajoules or 9.3 megajoules, and we're good. So that is how you would do a problem involving heating or cooling of a substance that goes through a phase change. This is a heating example, but a cooling would be done the same way. You would just be dropping the temperature until you got to the phase change, and it would be a negative value on the heat when you were done, is the only difference.